And here we go with the final unit of the year review. I hope you guys are having a great day, and let's do it. So for number 1, a statistically minded toll collector wonders if drivers are equally likely to choose each of the 3 lanes at his toll booth. He selects a random sample from all the cars that approach the booth when all 3 lanes are empty, so that the driver's choice isn't influenced by the cars already at the booth. Here are his results. Left lane 137, center lane 159, right lane 169. These are the observed counts. All right, which of the following is the appropriate alternative hypothesis? So we are trying to figure out if these lanes are equally likely. Our null hypothesis would be that the distribution is all equal, meaning that there's no difference, right? There's an equal to sign. All of them are equally likely. All right, the alternative would be that they are not equally likely. All right, so the null hypothesis is that they are all equally likely. And then the alternative would be not equally likely. So when I look at the answer choices, we're looking for the alternative hypothesis. So the observed number of cars is equal. I'm never talking about the observed. I'm always talking about the actual population of what happens, right? So I'm not talking about the observed number necessarily. We're talking about the proportion of cars choosing each of the 3 lanes are equal. That is our null hypothesis, okay? D, the proportion of cars choosing at least one of the lanes is different from the proportion choosing the other 2 lanes. Now, that is basically saying that they are not equally likely, okay? So it's just another way that you can write it. E says the proportion of cars choosing each of the 3 lanes are all different. Here's the thing about that. It does not have to be that all 3 of them are different. It just has to be that one of them is different. So like if the right and the center lane are 40% each and the left lane is 20%, that's fine. That just shows that they're not equally likely, okay? 2 of them are equally likely, but the third one's not. So we're seeing that the proportion of the cars choosing at least one of the lanes is different from the proportion of cars in the other 2, okay? So that's how we would write the alternative hypothesis there. Now, just so you know, on a free response, you literally could write the null hypothesis is that all lanes are equally likely to be picked. The alternative is that all lanes are not equally likely to be picked. That would be fine as well. You don't necessarily have to say the proportion of cars that pick whatever. You don't have to always necessarily say that. You can say that it's either all equally likely or not equally likely. Number 2, this is the same situation. Which of the following is the correct expression for the chi-squared goodness of fit test in this situation? So chi-squared, it looks like we're trying to find chi-squared here, is the observed minus the expected squared divided by the expected. So in this particular situation, we had a total number of cars that were being observed. We had 137, 159 plus 169, and so that total is 465. That's the total. So when I divide that by 3, when I divide 465 by 3, I get 155. So I should have expected 155 in each of these lanes. So observed, I've got my left lane, my right lane, or my center lane, my right lane. So observed, 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 observed. Okay, all of these look like they have the observed in the right spot. Expected should be 155 for each of them. 155, 155, 155, 155. That's all good. On the bottom of the fraction, I need the 155 again for the expected for each of them. So that's why I can mark out B, I can mark out D, and I can mark out E, okay? Now, the difference between A and C. on A, they actually add all of those observed minus expected divided by expected. They don't square each time. They square at the very end, and that's the problem with A. If you see on C, they're squaring each time. That's the reason that C is the answer. Okay. Alrighty, let's continue. Number 3. Which of the following is a condition that must be met in order to carry out a chi-squared goodness of fit test? So we have 3 conditions: random, independent, and the large count condition. Now remember, it's not the normal condition, it's the large count condition, and that is that all expected counts have to be greater than or equal to 5. So the population must be normally distributed. Heck no, this is a right-skewed chi-squared, so that's not right. The cell counts for our sample have to be approximately the same as the expected counts. They don't have to be. We would love for them to be, but they don't have to be. The observed cell counts must be greater than 5. Nope, nope, nope. It's the expected counts must be greater than or equal to 5. Okay? It's actually or equal to. That is a typo I need to fix. Sorry about that. And then E is, that's not true. So the answer is D. Alrighty. Number 4, 5, 6, and 7 will all come from this particular problem. A company manufactures special plastic containers that hold specified volume of hazardous material. Some containers do not meet specifications and are required by the company's customer, as required by the company's customer, because they are either too small or too large. Let's see, are there differences between the sizes of containers produced by the 3 shifts? Here are the results of inspecting 500 randomly selected containers from each of the shifts. These are our observed counts. Okay? Which of the following is the appropriate null hypothesis? All right, so first thing we need to do is decide what kind of test do we have going on here, all right? So here's what we've got. We've got 3 different shifts, all right? We've got an 8 a.m., a 4 p.m., and a midnight. That means we have 3 populations, and we are seeing if we have conformed to specifications within those. So that's one variable. So we have 3 populations and 1 variable. So when we're trying to see if different populations are the same or different, that would be a chi-squared test for homogeneity. So in that situation, our null hypothesis would be that the distribution for all populations is the same, and the alternative would be the distribution is different. Okay, so now let's look at our number 4 here. The null hypothesis is not about the expected counts, it's not about the observed counts, it's about the distribution. The distribution of the variable conformance to specification is the same for all 3 shifts. Pretty much sounds like the distribution of all populations is the same, okay? Conformance to specification is associated with shift. That would be more if we were doing a chi-squared test for independence. That's when we're talking about association. The proportion of containers, that is the same. That's not necessarily what we're looking for. We're not looking for proportion. We're looking at the distribution of everything is the same, okay? So that would be C. Which of the following are the degrees of freedom for this distribution of the chi-squared test statistic in this situation? Degrees of freedom is row minus 1 times column minus 1. We have 3 rows minus 1, 3 columns minus 1. That's 2 times 2, which is 4. That is D. Which of the following represents the expected count for the cell too large and midnight? Too large and midnight. So too large and midnight. So to find the expected count of any particular cell, you need to do the row total times the column total divided by the table total. The row total for midnight is 500. The column total for too large is 95. And then we need to divide by 1,500. So we can immediately take off A, B, and D. And then on the top, we just need to multiply 500 by 95. So the answer is E. Number 7 is an extremely tricky question. You have to be careful about what it tells you this table is. It says a test of the hypothesis in question 4 is statistically significant at the alpha equals 0.05 level. First of all, what does statistically significant mean? That means that we have rejected the null hypothesis. And why do we reject the null hypothesis? That's our p-value is less than our alpha value, okay? So statistically significant, we have rejected the null hypothesis. Now, carefully, below are the individual components of the chi-squared statistic. These are not the observed, these are not the expected. These are the chi-squared contributions for each of these cells, all right? That means this is the observed minus expected squared divided by expected for each individual cell, okay? So, based on these components, the original two-way table, which of the following is true? So what that means is, for example, the 8 a.m. shift that had too large, there was a big difference between the observed and the expected in that category. The 4 p.m. shift and too small, there was no difference. In this particular situation right here, the observed equaled the expected, okay? The thing that you have to be careful about here is even though, like, for example, this has a big difference, right? There's a big difference in observed and expected. But here's the thing, you don't know which one was bigger, okay? Because we square the difference, we don't actually have any idea or any way to know which one was bigger. So we have to be very careful there. We just know that they're different, but we don't know which one is the bigger one, okay? So based on these components, the original two-way table, which of the following is true? The observed count of containers produced by the midnight shift that were within specifications. Let me erase this. The observed counts of containers produced by the midnight shift that were within specifications, so I'm talking about this cell right here, was very close to the expected number. Well, look at that difference, right? Look at that chi-square contribution. Very small chi-square contribution. That means there was a very small difference in the observed and the expected. So that one looks like it's going to be right. But let's continue and see why the other ones are not, okay? The next one says, the observed count of containers produced by the 8 a.m. shift that were within specification, so we're talking about this one, was much higher than the expected number. Okay, I don't think that the observed and the expected are going to be very different when my chi-squared contribution is 0.132. That's a pretty small difference in that situation. So that would definitely not be true. Okay, the next one. The 4 p.m. shift has the smallest proportion of containers that are either too large or too small. They're trying to get you here. Okay, 4 p.m. has obviously the 4 p.m. shift, they're doing a really good job of getting exactly what is expected, okay? But that does not mean that they have small proportions of containers that are too large or too small. That's not what that's saying. This is saying that there's a small difference between what is observed and what is expected, okay? So careful. These are the tricky ones. And then D, the 4 p.m. shift does not produce any containers that are too small. That is completely incorrect. What that 0 means is that the observed equaled the expected. They might be producing 4,000 containers that day. I don't know, but they are producing exactly what is expected in that category. That's what that means. Most of the containers produced by the 8 a.m. shift that were within specifications were closer to being too small than being too large. I have no idea which way this was actually trying to go. I don't know if they were close to being too small or too large. I don't have that data. I don't have the data that shows how far it is to be too small or how far it is to be too large. So I really don't have any idea on that, if that's true or not. Okay. So number 7, big, tricky question. Make sure you're careful on that. Alrighty, number 8. We're going to use this for number 8 and 9. Are all employees equally prone to having accidents? To investigate this hypothesis, a researcher looked at a light manufacturing plant and classified a random sample of accidents by type and by age of the employee. So we have our observed counts here. These are our observed. Here are the expected counts for this table under the null hypothesis. These are the expected counts. What is the individual component of the chi-squared statistic for the under 25 and burn? Under 25 and burn. All right, so I'm looking there. And so what we need to find here is the observed minus expected squared divided by expected. The observed is 17. The expected is 7.9. We square that, and then we divide by the expected, which is 7.9, and we get 10.48. A chi-squared test for the above data gives a test statistic of 20.78. If we test at alpha equals 0.05, which of the following is the appropriate conclusion? In order to make a conclusion, I need a p-value. When you are given the chi-squared test statistic, you can get the p-value by using chi-squared CDF. If I go to chi-squared CDF, it's going to ask me for the lower boundary. The lower boundary is the chi-squared value. The upper boundary is infinity. Remember, we always are going from 0 to infinity here. And so our chi-squared test statistic is 20.78, and we're finding this particular area here, which will be the p-value. Degrees of freedom. Degrees of freedom are row minus 1 times column minus 1. And so the rows, there were 2 rows minus 1. There were 3 columns minus 1. So we have 1 times 2. So our degrees of freedom are 2. Okay. And when we plug that in, we get a very small p-value. It is 3.07, or is that an 8? I don't really know. It's one of those numbers. It's a very small number, though. And that is definitely less than 0.05, so we're going to reject this null hypothesis. So our conclusion here is we're going to reject, so we can mark off D and E. And we reject because we have convincing evidence. We have convincing evidence. Now, what do we have convincing evidence for? The alternative hypothesis. And the alternative hypothesis is that that the accident type is not independent of age, basically meaning that there is, in fact, an association. The null hypothesis would be that there is no association. The alternative is that there is an association. If there is an association, then that means that they are not independent of each other. Okay, so that is why B is the answer. Number 10. A survey was conducted to investigate whether alcohol consumption and smoking are related. In an SRS of 300 smokers, 196 said that they had consumed alcohol at least once in the past week. In an independent SRS of 300 non-smokers, 159 said that they had consumed alcohol in the past week. If P sub S is the proportion of smokers in the population that have had a drink in the past week, and P sub, I'm not sure what that says, RS is the corresponding proportion of NS, non-smokers in the test. We are going to test these hypotheses. P sub S minus P sub NS equals 0 against the two-sided alternative that produces a test statistic of Z equals 3.07. Okay, by the way, they are using here a 2-prop Z test, and they get a p-value of 0.002. If we had instead analyze these results with a chi-squared test of homogeneity, what would we have gotten for the test statistic and the p-value? So what we need to do is we need to take all that data and we need to convert it to a two-way table, okay? So if we do smoking versus drinking, so they're non-smokers, right? Smoking versus drinking. We have yes that they smoke and no that they do not smoke. Yes, they drink and no, they do not drink. So in an SRS of 300 smokers, so we have 300 smokers. So there's 300 that say yes that they smoke. And then 196 said that they had consumed alcohol. So 196 said that they had consumed alcohol of the smoker group. So 196 said that yes, they consumed alcohol. And in an independent SRS of 300 non-smokers, 159 said that they had consumed alcohol. Okay, now we can fill out the table. So we have 600 total. We have 104 that are smokers but do not drink. We have 141 that are non-smokers and do not drink. And then 355 total that say yes, they drink. 245 that say no, they do not drink. And then we have our big total of 600. So we're going to use the matrix. We're going to go to second x negative 1. Second x negative 1, and this is a 2 by 2 matrix, and we are going to put in our actual observed counts. You do not put in the totals, and then you'll go to stat test C for chi-squared test, and your degrees of freedom would be 1. Degrees, I don't even remember if it asked for that or not, but it would be 2 minus 1 times 2 minus 1, so it would be 1. And you hit enter, and it's going to give you your chi-squared test statistic, which is 9.42, and your p-value, which is 0.002. So the answer is A. Alrighty. And free response. Are you more likely to be allergic to house dust mites if you are born in a certain season? Recent research suggests this might be true. Below are the birth seasons of 500 randomly selected people who are allergic to horse dust mites, along with the expected proportion of people born in each season, based on data from the entire population. Do these data provide evidence that people who suffer from this allergy have a different birth season distribution? Support your conclusion with the appropriate test. So what I've got here is I've got the number of observed allergy sufferers per season, and I have the proportion that it's of births in general population. So I have the proportion of births in each season. So these are the expected proportions for their birth, okay? And so this should be we're trying to see if this matches. Does this distribution of birth proportions match the proportion of the allergy proportions? So I do only have one sample. I am only looking at one variable, whether they are suffering from allergies or not. So this is a goodness of fit. I'm trying to see, does this distribution fit the allergy suffering distribution? So state, we will test at alpha equals 0.05. It didn't give us anything else. The null hypothesis, the stated distribution of births is no different for allergy sufferers. The alternative is that the stated distribution of births is different for allergy sufferers. Plan, random, we have an SRS of 500 people who have dust mite allergies. That's just so that we're all looking at the same data, basically. We're looking at the same type of population. 10% or independent, this is same thing. 5,000, sure, I'm sure there's probably more than 5,000 horse dust mite allergy people. Large counts, all right, this is where we need to check our expected counts. So if we tested 500 people and 30% of the general population is born in winter, then we should expect 150 to suffer from this allergy. If we have 22% of the population is born in the spring, then we should have 110 of these horse dust mite sufferers should be born in the spring. 24% in the summer, that means we should have 120 that should have this allergy that were born in the summer. And then in the fall, we have 120 there as well. All of our expected counts are greater than or equal to 5, so the chi-squared statistic applies. Okay. We are going to use a chi-squared goodness of fit test. What that means is we're going to go to stat edit. Chi-squared goodness of fit uses L1 and L2. In L1, you need to put your observed values. In L1, you're going to put your observed values, which is going to be 117, 105, 145, 133. And in L2, you're going to put your expected values, which you just found, and that goes into L2. And then you'll go to stat, test, D for chi-squared goodness of fit test, and you will get your chi-squared test statistic, your p-value, your degrees of freedom were 3. There's 4 categories, -1 is 3, and that's what you get. Conclude. Our p-value is 0.003. That is less than our alpha of 0.05. We will reject that null hypothesis. There is convincing evidence that the stated distribution is different for these allergy sufferers. So it appears that whenever you are looking at dust mite or horse dust mite allergy sufferers, they have a different distribution than the rest of the world for when they were born. So maybe if you're born in a specific time, maybe you are more or less likely to have this allergy. Okay. And our final problem. So on number 12, I did ask you guys to make a little change here, and you'll see that here in just a second. Which modern electronic devices do you care most about? A simple random sample of 120 people were asked 2 questions: their age, and if you had to give up one of the following 3 electronic devices for 3 months, which would you choose to give up? Only people who actually owned all 3 devices were interviewed. Here are the results: cable TV, home internet, or cell phone, and then they've got age categories here as well. All right, part A is what I asked you guys to change. In the blank table below, provide the, not the conditional distribution, provide the expected counts. And then you don't have to do this whole summary thing here, okay? So what we're going to do, we're going to plug these observed counts into the matrix. So you're going to go to second x negative 1, go over to edit number 1. This is a 3 by 3. And you're going to plug your data in. Then, after you plug your data in, you can go to stat test C for chi-squared test, and you can hit calculate. Now, I know when you hit calculate, you're getting the chi-squared test statistic and the p-value and all that. But at that same moment, your calculator put your expected values into the B matrix. So now if you go back to second x negative 1, go ahead and go over to edit, but go to number 2, the B matrix. Go over to number 2, the B matrix, and you will find there under the B matrix your expected counts. And then you can write them down here. Okay. Alrighty, this was one sample. We had a random sample of 120 people. We asked them 2 variables, their age and what service they would give up. So this is a chi-squared test for independence. And here's our state plan to conclude. I know it just says provide the appropriate statistical test, but this is the whole shebang here. So state we will test at alpha equals 0.05. The null hypothesis, the age is not associated with what device people would be willing to give up, basically saying that there's no association here. The alternative is that there is an association between age and what device they would give up. Plan, we have an SRS of 120 people. There's definitely more than 1,200 people in the population. Our large count, all of our expected counts are greater than or equal to 5. We can see the matrix above. Okay, all of our expected counts were greater than or equal to 5, so our chi-squared statistic applies. We're doing a chi-squared test for independence. We get a chi-squared statistic. Remember, you might still be on the matrix, right? To get back to the chi-squared, you just go back to stat test C. That'll take you right back to your chi-squared statistic and your p-value right there. P-value is less than alpha, so obviously we know what to do. P-value is low, reject that null hypothesis. There is convincing evidence that age is associated with what device people would be willing to give up. There you go, ladies and gentlemen. You are going to do a fantastic job on the test. 10 multiple choice questions, a couple of free response questions, easy peasy, lemon squeezy. You're going to get a great grade on that last test of the year. See you later.